equation, right? From these n equations, you solve for a1, a2, a3, an, and once you have solved for a1, a2, a3, an, you plug into this original equation the value of a1, the value of a2, value of a3, value of an, and you get a nth order differential equation. Why would it be nth order? Because you know, in solving for a1, a2, an, the nth order derivative will also appear. Right? This, when you differentiate n times, the nth order derivative is inevitable. That appears in the solution. Right? And when you plug into this, you will get a nth order. The highest order derivative would be of order n. So you get a differential equation of order n. For example, I have, let's say, a family of curves of the following kind. Y is a e power 2x plus b e power 3x. Suppose I have a family of curves y equal to a e power 2x, b e power 3x, where I treat a and b as arbitrary constants. A and b are arbitrary constants. If a and b are arbitrary constants, then that means I have to eliminate a and b. You would then expect the order of the differential equation to be 2. Alright. Let me differentiate this with respect to x once. I get like a dy dx equal to 2a e power 2x plus 3b e power 3x. When I differentiate once, this is what I get. Let me differentiate a second time. When I differentiate a second time, I get like a d2y dx2 equals 4a e power 2x plus 9b e power 3x. Now, from this simultaneous equation, you can solve for a and b in terms of dy dx, d2y dx2 and e power 2x and e power 3x, right? You can solve for a and b, and once you solve for a and b, you go back to the mother equation and plug in those values of a and b that appear in terms of the derivatives, the second order derivatives, and other things, other functions involved. Once you do that, once you plug in a and b into this, you get the required differential equation representing the entire bunch of curves with a and b as parameters. Right? Although, as far as this is concerned, I'll show you, we don't have to do all this in one shot. I can just close my eyes and tell you what the differential equation would be. But then let me come to that point. I just wanted to tell you how to do in general, but for this particular situation, all of this is not required. I mean, I can just tell you, if you eliminate a and b, it's going to be d2y dx2 plus 5 dy dx plus 6 equal to 0. This is what you're going to, minus 5 dy dx plus 6 equal to 0. When you eliminate a and b, this is what you're going to get. But I'll tell you how you get that without having to think too much. But in general, this is the broad blueprint involved in finding the differential equation for a family of curves. You should very easily identify the number of arbitrary constants involved when you constitute the differential equation, and the order of the differential equation related to the arbitrary constants involved. And in fact, once you eliminate a and b, you get the differential equation, and then this is said to be the solution to that differential equation. This is then said to be the solution to that differential equation. Alright, and this then becomes the general solution to the differential equation. See, when you eliminate a and b, you get the differential equation. You get the differential equation. But then when I say solve the differential equation, that means I need a relationship between x and y. This then would be the solution to that differential equation. This then would be the solution to that differential equation. You know what I'm saying? And then it brings us to yet another important aspect of differential equations, the solution to a differential equation of order n. Write down the general solution the general solution to a differential equation of order n must necessarily contain n arbitrary constants. Right. So once I constitute the differential equation, I can say that this is the general solution to that differential equation. Now there could be a particular solution to that differential equation. A particular solution would mean when, let's say, I assign a certain value to b. Let's say I put b equal to 0. Then a e power 2x will satisfy that differential equation. So y equal to a e power 2x is also a solution to that differential equation, but it's not a complete solution. It's a particular solution. I can also say y equal to 5 a e power 2x 6 e power 3x, 5 e power 2x 6 e power 3x. That will also satisfy the differential equation, because that differential equation would be satisfied for all pairs of a and b that you choose, right? So that differential equation would be satisfied by, let's say, a equal to 2 and b equal to 3. But if you put a equal to 2 and b equal to 3, then that also is not the general solution to the differential equation. That's a particular solution to the differential equation. You may put b equal to 0 and a equal to 5, or a equal to 0, b equal to 6. That will also be a solution to the differential equation, but it will be a particular solution. It will not be a general solution to the differential equation. Are you all there with me on this? Right? So you clearly understand the difference between a particular solution and a general solution. In most occasions, we are seeking the general solution in which the number of arbitrary constants should necessarily match the order of the differential equation. Alright, even though you may have arrived at a solution, it may or may not be the general solution. You will have to check that by looking at the number of arbitrary constants that appear in the differential equation. Alright. Now the various kinds of differential equation. Let's come to business. Various kinds of differential equation. One kind of differential equation that you have solved all along in your +2. First of all, to begin with, we are looking at linear differential equations. We are looking at linear differential equations of first order. When I say linear means the degree is 1. When I say linear means the degree is 1. I am talking of degree 1 and order 1. Linear differential equations of first order. Various kinds of linear differential equations of first order. Let's examine and categorize those differential equations. Okay. The ones that you have already solved are those in which the variables were readily separable. The variables were readily separable. Those are the differential equations that you have solved umpteen times. For example, dy dx equal to some function of x divided by some function of y. If a differential equation can be written like this, then realize that the variables can get easily separated here. I have then like a 5i dy equals fx dx. The variables have got separated very easily without too much of problem, and then you can go ahead and integrate You can go ahead and integrate, and what emerges then would be a relationship between y and x. And how many arbitrary constants would appear here? Just one. It's a first order differential equation. It's a first order differential equation. So one arbitrary constant would appear in its general solution, But if you put c equal to 0.6, then that would be a particular solution. Alright. So something like dy dx equals ln x by e power y, for example. Variables are separable here because I could write this as e power y dy equals ln x dx, and I can integrate this. E power y then would be x into ln x minus 1 plus an arbitrary constant. Right, when you integrate ln x, this is what you get, x into ln x minus 1. Integrate by parts ln x, right? This is what. So this then becomes the general solution to this differential equation, in which the variables are so easy to sieve with c as an arbitrary constant. That's the solution to this differential equation. Now, there could be situations where you'll have to perform a little bit of manipulation to separate and sieve the variables. Right? For example, can I wipe this off? You could have a differential equation of the following kind. Dy dx, let's say, is some function of ax plus by. Suppose dy dx is some function of ax plus by. A and b are fixed constants. For example, you have dy dx equal to sine 2x plus 3y, right? Something like this. In this case, it doesn't become obvious what to do. The variables x and y by themselves are not separable right away. But what you could do is, you can trigger another variable. What you can initiate is the following. You can bring in a variable, call it z, which is ax plus by, and constitute a new differential equation. If I differentiate z with respect to x, I get like a dz dx equals a plus b dy dx, right? When I differentiate with respect to x, I bring in a new substitution, a new variable z, and I'm calling that ax plus by. So dz dx becomes a plus b dy dx, and dy dx can then be written as dz dx minus a. So this dy dx I write as dz dx minus a divided by b, right? This dy dx could be written as dz dx minus a divided by b, and that's equal to f of z. So now, instead of being a differential equation in x and y, it becomes a differential equation in x and z, right? So we may then want to call this as b times fz, and when I transpose this on the right hand side, a plus b times fz is dz dx, and then I can say dz by a plus b times fz equals dx, and then I can see the variables have got separated, z and x have got separated. Then depending on whatever fz is, I could integrate this, and bring in an arbitrary constant c in the general solution of this differential equation. And then once I solve z in terms of x, in the final expression, I can then bring back ax, plus by. I can replace then in the final solution all the z's wherever they appear by ax plus by, and I would have the general solution appearing in terms of x and y alone, right? So this is what you would want to do here, right? 2x plus 3y as z, and you would have a differential equation involving z and x, in which z and x could be separated. You can solve for z in terms of x by integrating, and then eventually replace the z by 2x plus 3y. right? So even sometimes when it's not served on a platter to you, you can carry out a little bit of an adjustment here and there and may want to convert it into a differential equation in which the variables could get sieved. All right? The next most common type of differential equation that we are going to encounter is the homogeneous differential equation, the homogeneous form. The homogeneous form of the differential equation. Essentially, if I can write dy dx, as a function of y by x alone, if I can write dy dx as a function of y by x alone, then that form of the differential equation is called a homogeneous form. It's called a homogeneous form. Now, let me tell you, for example, dy dx x squared y plus xy squared divided by x cubed minus x squared y, for example. Right. This would be homogeneous, you know. Every time you have ratio of two functions, this is a function of x and y and this is also a function of x and y, this would be homogeneous under two conditions. Two conditions would be required. One would be that both numerator and denominator should be of the same degree. See, for example, 2 plus 1, 3. That means, you know, first of all, this should be homogeneous and this should be homogeneous. This is homogeneous. Why? Because the powers of x and y in each term, add up to 3. This also is homogeneous. This is homogeneous because the powers of x and y in each of the terms add up to 3. So this is homogeneous of degree 3. This is homogeneous of degree 3. So both numerator and denominator should be homogeneous and should be of the same degree. Should be homogeneous and should be of the same degree. So in this case, this is homogeneous. Why? Because the powers of x and y in each of the terms would add up to the same number. That's why this expression is homogeneous. This expression is also homogeneous because the powers of x and y add up to the same number. In this case, the degree of homogeneity is 3. In this case also, the degree of homogeneity is 3. So they should be homogeneous and should be of the same degree. If that happens, then you can convert this into a function of y by x alone. If this condition is met, you could explicitly convert this into a function of y by x alone. How? In this case, I can divide either by the highest power of x permissible or the highest power of y permissible. X cube is the highest power of x permissible, y cube is the highest power of y permissible. Either way, suppose I divide both numerator denominator by x cube. Alright, so when I do that, then I get like a y by x plus y by x whole squared divided by 1 minus y by x when I divide by x cube, both numerator and denominator. Do you then realize that it's become a function of y by x alone? It's become a function of y by x alone, is it not? So this becomes a differential equation which is homogeneous because dy dx is a function of y by x alone, is a function of y by x alone. The important condition is if I have ratio of two polynomials in x and y, they should be both homogeneous and should be of the same degree. Then I can look upon this as a homogeneous differential equation. Now, for homogeneous forms, all that you need to do is you need to take y by x as some z, y by x as some z. That means y equal to some z times x, y equal to some z times x, and then write this as dy dx equals x dz dx plus z. dy dx would be x dz dx plus z, right? And then this dy dx could be substituted here by x dz dx minus z plus z, right here. So write this dy dx as x dz dx plus z equal to f of z, equal to f of z. Y by x is z, and then you have like a x dz dx is f of z minus z, right? And then you can bring in f of z minus z below this dz. The variables are now separable. The variables have got separated. You can then integrate. You can integrate this function, an arbitrary constant would appear, and that would be the general solution to this homogeneous differential equation, right? And it's not like you would always have polynomials. There could be slight departure from these polynomials. It could be something like this also, where a polynomial may not be involved. In this case, it was a ratio of two polynomials, a homogeneous expression. We could also have had something like this. Dy dx, for example, is sine of y by x. This also I would term as homogeneous. This also I would categorize as homogeneous. And like before, I can put y by x as z. I could write dy dx as x dz dx plus z, right? See, same thing. I could say y equal to zx, and then the dy dx could be written as dz dx x plus z equal to sine z, and sine z minus z. So dz by sine z minus z equals dx by x, It's another story that sine z minus z may not be integrable. That's another fact. I mean, so don't go ahead and give it to your teacher in school. Integrate 1 by sine z minus z. 1 by sine z minus z cannot be integrated by angels also. Okay. So this is non-integrable, and let me tell you, not all differential equations may have solutions, may not have solutions. That's a possibility. Don't expect a differential equation to always have a solution. May not have a solution. All right. So this is what you do, right? Each time you have dy dx as a function of y by x alone, you close your eyes and put y equal to some z times x and proceed like I did. All right. Now, the other kind of differential equation that would be again very common in as far as real life applications go, and they would appear large number of times in physics and other sciences, is what's called the linear differential equation. It's just called the linear differential equation. The form of this differential equation, is dy dx plus p times y is q, where p is some function of x and q is some function of x. P is some function of x and q is some function of x. Now, to solve this differential equation, let's multiply both sides by e power integral p dx. P is some function of x, q is some function of x. Let's multiply both sides by e power integral p dx. E power integral p dx dy dx plus py e power integral p dx is q e power integral p dx. Now the left hand side is really the derivative of the product of two functions. Observe that the left hand side is like a ddx of y e power integral p dx. Notice this. Derivative of first function into second function is this term, right? Derivative of y with respect to x into this function is this first term, right? Derivative of second function, that means derivative of this into y, should then turn out to be this function. What is the derivative of e power integral p dx? What's the derivative of e power integral p dx? Chain rule, differentiate with respect to integral p dx, you will get e power integral p dx, and differentiate integral p dx with respect to x, you will get p, isn't it? When you differentiate integral p dx with respect to x, you will get p, yes or no? So into p. So would you mind believing that this p e power integral p dx, this p e power integral p dx is actually the derivative of e power integral p dx. So we have in this expression derivative of y with respect to x into e power integral p dx plus derivative of this part is derivative of e power integral p dx into y, derivative of the product of two functions. What are the two functions? Y and e power integral p dx. Sounds alright? Right? And the right hand side becomes q e power integral p dx, q e power integral p dx. And now when you take this dx on this side and integrate both sides, then d of t is t, d of t, integral d of t is t. So we have like a y e power integral p dx is integral q e power integral p dx dx. That's the solution to this differential equation. That's the solution to this differential equation. I mean, then obviously p and q would be known to you. You would have to plug in p and q as is given and then integrate both sides. So y e power integral p dx is integral q e power integral p dx dx. After having integrated the right hand side, you would arrive at a constant of integration and you would get the general solution to the linear differential equation. You know what I'm saying? Now let's quickly illustrate a few of these linear differential equations. Look at the sheet which comprises the linear differential equations. For example, problem 1 in the sheet, part D, problems that contain linear differential equations of the form dy dx plus py equal to q. Problem 1, for example, 1 plus x squared